Hey guys, in this video I want to talk about the Lagrange inversion formula, which helps us to find the coefficient of xn in a formal power series. The proof is also covered in Wolff's textbook chapter 5, so you can also read Wolff's generating functionology if you want to, and I'm just going to go over the proof here in this video. And I learned this proof from Professor Irina in my combinatorics course. So, the theorem says that let phi x be a formal power series in X, and we have the initial condition that phi 0 equals 1. Then there is a unique power series U in X that satisfies, first, Ux equals X phi Ux, and second, the coefficient of xn in Ux is the same as 1 over n times the coefficient of x to the power of n minus 1 in phi x to the power of n. Now, this seems very abstract. Let's see how this formula is used in solving problems. So here's an example problem. Suppose we have a formal power series Ux, and we know the recurrence that Ux equals x times e to the power of Ux. Now, we're interested in finding the coefficient of xn in this formal power series. How can we do that? So the idea is to use Lagrange inversion formula. But to use that formula, obviously, we should first find phi, the function phi, right? So if we look back at the Lagrange inversion formula and this example problem, can you pause and think about what phi would be in this problem? I'll wait. Okay, so I assume you have to think about this problem. So phi u equals e to the power of u. Note that here I'm using the variable as u instead of x. But essentially, no matter what variable I use, say it's x or it's y, right? So these three things I wrote here describe the same function. So the choosing of variable is actually very arbitrary. I can also write phi n equals e to the power of n, where my variable is named Anna. So it's important to keep in mind that I choose u as my variable here. And why do I choose u? Because we already have an x here. We already have an x here, and I don't want to confuse you with x as the variable. Alright, so phi u equals e to the power of u. And why would this work? Alright, so if we substitute ux as u, right, then we will see that u, from the red equation, we will see that u equals x to the power of eu. And we can rewrite this as x times phi of u, because this is how we define u. And what we have here is exactly what it exactly satisfies the first condition. And what we have here satisfy this condition in Lagrange inversion formula. So since one is satisfied, we can now apply 2 to solve the problem, right? Okay. So we are interested in finding the coefficient of xn. And this expression is exactly the left-hand side of the second equation. So now the problem becomes, what is this expression? Note that here I changed the variable for the function phi as x instead of the u here. Just keep in mind that although it's different names for the variables, it describes the same function. So what would this be? Well, by our definition of phi x, this is just, well, we're looking for the coefficient of x to the power of n minus 1 in the expression, in the expression e to the power of xn. That's what we're looking for. Okay, so we know that the expansion of e is 1 plus x squared over 2 plus x to the power of 3 over 3 factorial plus dot dot dot. And we can write this in the summation form, right? Yeah. So, this is actually ex. Yeah. So, if we raise this summation to the power of n, we will have something like this. And if we are interested in finding the coefficient of x to the power of n minus 1 in this summation raised to a power, it's actually similar. It actually has a combinatorial interpretation. So let me just write this out. Alright, so yeah, how can we find the coefficient of x to the power of n minus 1 in this product, right? And maybe let's just expand the product a bit, right? What is it? What does it look like if we expand it? Right? So when I write out the summation, it's something like this. So we will have 1 of those, 2 of those, 3, and dot 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 dot, and then we have our final, the nth one. So there are n such parentheses in total, right? N such closed parentheses in total. And how can we get n minus 1? Well, if I pick 1 here and 1 here, all the ones, right? And then in the final one, I will pick the term with xn minus 1, which will have the coefficient 1 over n minus 1. Then I will get this. I will guess something with x to the power of n minus 1. However, suppose in the first param I pick x, then I will get 1 times 1 over n minus 1 factorial times x to the power of n minus 1, which is 1 over n minus 1 factorial times x to the power of n. And this is not what we want, because we are only interested in finding the coefficient of x to the power of n minus 1. So the question becomes, how can we combine this different power, I don't know, 3 or 4 or k, 1,000. How can we combine those powers such that they sum up to n minus 1, and if they sum up to n minus 1, we are interested in this coefficient, right? So that's the question. So to be more formal, we can actually, so now we understand the question. To be more formal, we can write this expression as this. So if you recall the parentheses, we have n paren, right? So let's say for each paren, for parenth I I pick the power to be ki, right? So since we have n paren, we will have k1 up to km. So we will want k1 plus k2 plus all the way to kn sums up to n minus 1, because that's the coefficient we're looking for. Additionally, we have the constraint that all the powers has to be greater than or equal to 0, right? Because if you pick 1, then it's x to the power of 0, and then the power can go to very, very large, but you cannot have negative power. That's why we have the second constraint, right? And if we know what if we know what power we pick in each paren, then the coefficient would be this. Okay, so we got a nice looking expression, and this actually looks less daunting than much less daunting than the purple equation up there. So yeah, so this summation is also not easy to just solve algebraically, but it would be much easier if we can give it a combinatorial interpretation, right? So all those factorial down here reminds us of repetition. So how can we give this a combinatorial interpretation? Well, this actually reminds me of the multinomial theorem. So we're going to add this at the top, right? And then divide by n minus 1 factorial, so that we maintain the equality. And what is this? It's saying that, well, if we decide how to distribute the power of n minus 1 into those n parentheses that I showed you before, right? Then we will have this. We will have this. Yeah, so what is this? Can you think of a combinatorial interpretation for this? I'll give you some time to think about it. You can pause the video and then I'll review the answer. Okay, so I assume you have think about it. So you can actually think of this as distributing n minus 1 distinct marbles, because all the k's sum up to n minus 1, into n boxes. So why can we think of this? So first of all, you see that we have this k1 up to kn. So if we assign a non-zero number to each ki, it's like saying, hey, box I will give you ki many things out of the n minus 1 things, right? Now that we rephrase the problem, we see that this summation actually has a very, very simple form. Actually sums up to something very, very simple. So for each marble, for each distinct marble, it can go to any one of the n distinct boxes, right? So we have n choices for the first marble, n choices for the second marbles, and we have n minus 1 marbles in total. So this would be 1 over n minus 1 factorial times n to the power of n minus 1. And that's our final answer. If we look back, right, we only have this recurrent relation and we want to find the coefficient of xn, which looks like a daunting task, but with Lagrange inversion formula, we were able to reduce this problem to something that's much, much more simpler. And the final answer is absolutely cute. So this is the example of applying Lagrange inversion formula. In the next video, we will go about proving the formula.